will join us. So in terms of this week, by Wednesday, you have 2 sections due in MyLab Math. That's 4.1 and 4.3. We don't do 4.2, so don't go looking for 4.2. It's actually on linear modeling with actual real world data, and that belongs in a statistics course, which is why we don't do it here. You do need to get that exam scheduled with ProctorU. It is active, it is there. You should be able to see it and get it scheduled. That exam is due Sunday at 11:59. That's this coming Sunday. So get it scheduled, please. Any late fees are on your shoulders this time. So I did come in and got the discussion graded. I got the grades moved over from MyLab Math this morning. I went in and looked at all the quizzes and added some points back in. So I'm happy to report that almost everybody had a passing grade on the quiz this week, which was nice to see. Let's see what else. I downloaded the reviews to date. I have them graded, but I haven't provided the feedback yet. So I'll do that, excuse me, this morning after class. So we're moving along. That's a good thing to do. We're going to start chapter 4 today. It is literally our shortest chapter. It's only got 3 sections in it that we're going to do. So that's why we can do it before this exam. And that puts that next exam over chapters both 3 and 4. So that worked out nice for us. So chapter 4, now that we've decided what a function is in chapter 3, chapter 4 is about 2 specific types of functions: linear functions, meaning lines, and then quadratic functions, which we already know are those parabolas. So today we'll spend time on the linear functions, and then we'll spend Tuesday and Wednesday talking about quadratic functions, and then we'll review again for the exam on Thursday. So that's the plan. Today we're going to talk about the properties of linear functions. So the handout I emailed out to you starts off talking about lines, but I want to backtrack just a little bit in terms of formulas that you will need, just as a reminder. So these are formulas that you should have gained in another class. The main one being the slope formula, and that's y2 minus y1 over x2 minus x1, and that's how you find the slope of a line. It's the change in y over the change in x. So that's another way we work at change in y over the change in x. Now we've already used this when we talked about average rate of change, but it comes back into play here. And then also in terms of a linear function, the equation of a linear function would be f of x is equal to mx plus b, where m represents the slope and b would be the y-intercept. So that's your typical y equal mx plus b, just written as a function. Okay, so we will see horizontal functions, but we will not see vertical, because there's no such thing as a vertical function, because vertical lines fail the vertical line test. So in this case, just keep in mind you'll have a constant function, which would be a horizontal line, or you'll have a sloped line. So the very first question in the example, so example 1 is going to give us a bunch of points in a table format. So this is part A on that one. So it says we have 0, 1, 2, 3, 4 for my x's, and my y's are 9, 12, 16, 22, and 29. And what they want to know is whether or not this table of data represents a linear function. Well, in order to be a linear function, your slope has to be a constant. So it can't be like the average rate of change problems where we did, where it depended on which 2 points you picked, you got different slopes. This time, you have to have the same slope between every pair of points. Well, on the left column with the x's, we notice that we're simply adding 1. So to get from one point to another, we can add 1. We see that that's a constant. But over here, in terms of the y values, between the first pair of points, we're adding 3. Between the next pair of points, we're adding 6. So the change in y is not constant. So that means that this is not a function. It's not a linear function. So it may still be a function, but it's not a linear function. It doesn't represent a line. And I'm sure that if you actually physically plotted those points, you see that they don't lie along line. Example B on that one says that we have x again, and then we have f of x. This time we have -2, -1, 0, 1, and 2 is our x values. Again, we see that they're increasing by 1 each time, so it's good. The change in x is a constant. But the change in y is a 13, a 10, 7, 4, and 1. So in order for this to be a line, the changes in y also have to be constant. And sure enough, we notice between 13 and 10, the increase is 3. Between 10 and 7, the increase is 3. Same from 7 to 4 and 4 to 1. I'm sorry, it's not an increase, it's a decrease. You're decreasing by 3 each time. So it represents a line because that constant change, I'm sorry, the change is constant. The problem then says, well, once you've decided it's a linear function, this is a linear function, they want you to find the slope. Okay, so to find the slope, you can pick any pair of points. I'm going to come in and just use the top pair of points because they're just convenient. And we'll come in and find the change in y over the change in x. We already know the change in y is the -3, but let's prove it. So we're going to do the 10 minus the 13. So that's y2 minus y1 all over -1 minus a -2. And watch your signs carefully because if you're going to make a mistake, it's going to be a sign error. So the numerator gives me the -3. The denominator is going to give me a -1 plus 2, which is a +1, which gives me a slope of -3. So this simply means that as we move from one point to the next, we're going down 3 units and over 1 unit. And that's where your homework starts, is they're going to give you a table of values and ask you whether or not it's a linear function. If it is a linear function, then find its slope. This is a good section to start with chapter 4 because it's all stuff you've seen before, so that's nice. So any comments or questions on the first example? No? Yay! Example 2 really just picks apart a linear function. So we're going to be given a linear function, h of x is equal to a -1/4 x, and then it says plus 3. And again, you know that that's a linear function because you don't see any goofy function stuff. So there's no radical or cube roots, no absolute values. The exponent on x is a +1, and there's no x in the denominator. So that's how we know it's a line. You'll notice that it's in that y equal mx plus b format. Part A is simply asking you to find the slope and the y-intercept, then graph it. So what's the slope of this line?
Down 1/4.
Beautiful. Yep. Down 1. And by over, you mean to the right, I assume? Because we always move to the right.
Or up 1 to the
yes.
Or it could be up 1 to the left right.
Yeah. And you'll never hear a math instructor, hopefully, talk about it from that point of view. And the reason is because we really want you to look at this from left to right, never right to left. We always move left to right. But you're correct. You can go the other direction with it. What's our y-intercept?
+3.
Yep. So 0, 3. The y-intercept is where we're going to start our graph. So we'll go up to a +3 and make a point. That's our y-intercept. And then from there, we're going to go down 1 and over 4. So if I go down 1 and over 1, 2, 3, 4, it's the next point over here. And your line looks something like that. So and again, that's stuff that you've gotten from way long ago. You actually start talking about lines all the way back in middle school. So they laid groundwork for lines a long time ago. Part B on that problem is simply asking you to determine whether the linear function is increasing, decreasing, or constant. Well, when I look at this, as I'm walking from left to right, which direction are we walking, uphill or downhill?
Downhill.
Yep. So this is decreasing. It's a decreasing function. And the slope is actually telling that. So a negative slope is what's telling me that it's decreasing. So negative slope tells us that it's decreasing. The picture also tells me that, but if I didn't graph it, the slope alone would tell me that. And it's decreasing all along its length. So tying into what we did in the previous section or chapter, then it's decreasing from -infinity to infinity. You don't have to write that because it's assumed because it's a line. So part C on that one says determine the average rate of change. Determine the average rate of change. Well, the average rate of change is the change in y over the change in x, and for us, that's a constant. So our average rate of change is equal to the slope which we already said was a negative 1, 4. So they're just trying to tie the concepts from this chapter or section in with the previous concepts that we've talked about. Any problem with that? The easiest problem you're ever going to have. So let's put those on the exam. And then the next problem is a little different. It kind of comes out of the blue if you ask me. So you're given a picture, and the picture has on it 3 linear functions. So there's one that's sitting up here at 12. So this is up here at 12, and this is h of x. So h of x is the red line. You have another one that's down here at negative 5. And that one is g of x. So those are both constant functions. And then you have another one that is actually a sloped line that's cutting through. It's cutting through something like this. They label this point. So this point is over here at negative 4, negative 5. The y-intercept right here is at 0, 4. And then this point up here is at 3, 12. And this function is f of x. So I have 3 functions, 2 that are constant, they're horizontals. And then I have another one that's a sloped line that's sitting in there. And they ask us a bunch of questions about this picture. And I think the questions are a little confusing. So that's why we're talking about this one. So part A on the problem asks us to solve a negative 5 is less than f of x, which is less than 12. So negative 5 is less than f of x is less than 12. So because it's dealing with f of x, all I'm going to look at is the black line that's on the board. And what they're really asking me is, where is the y values? Because that's what f of x represents, between negative 5 and 12. And that's what the question's asking. Where are the y values of the picture between negative 5 and positive 12? Okay, well, the y value of negative 5 just happens to be the bottom horizontal line, and the y value of positive 12 is the top horizontal line. So they're asking, where is it between those two? Well, the y values are between a negative 5 and a positive 12 as we go between this point and this point. So we're going to answer in terms of the x values. So our answer is when x is between negative 4 and the positive 3. So these are the x values. So when x is between negative 4 and positive 3, the output y values are between negative 5 and 12. So you can write it as an inequality, or you can use your interval notation here and go from negative 4 to 3 with parentheses because of the inequality. And I think these are a little bit confusing. Any comments or questions? Okay. Part B on the question asks me to solve f of x equals h of x. So what this is really asking me is to find the point of intersection. This is where the two functions meet, where they cross each other. So f of x is the slanted line, h of x is the horizontal on the top, and these guys meet at this point 3, 12. So to answer the question is x equals 3. Notice again, I'm just picking on the x values because this is already telling me something about the y values. So when I solve the equation, I'm going to get just x equals 3. So again, the answer is only the x value. Any comments or questions about that? Because you're going to do one really, really similar to it. Okay, part C on that one says solve g of x is less than or equal to f of x. So this one comes back to an inequality statement. So where is g of x less than or equal to f of x? So this is literally asking me, where is g below f? So where is g below f? So I have to come back and look at my picture. G of x is the bottom red line. F of x is that black one that's sitting in there. So I want to know where G is below it. Well, isn't the red line below that black sloped line all this distance? So everywhere along in here, that's true. So the red line is below the black line here. So isn't that all the x values that are bigger than that -4? So G is below F whenever x is greater than or equal to -4. I'm picking up a greater than or equal to because that's what they've got in terms of their answer, is the equal to. And to write that in interval notation, we're going to go from -4 to infinity. So we're simply saying, starting at -4 off towards positive infinity, the function g of x is below the function f of x. Huh. Okey-dokey. There's one more part to the question, or the example. So part D on that question asks us to solve h of x is greater than g of x. So h of x greater than g of x. Okay, well, h of x is the top horizontal line and g of x is the bottom horizontal line. So they're simply asking you, when is that top red line above the bottom red line? Well, isn't that always true? I mean, isn't this one always above this one? And again, you're talking about y values. So the y values here are always larger than the y values here. So that's true along the whole length of the picture. So then our answer is going to be from -infinity to infinity. It's always true. So you're going to do 2 of these. They're very similar in nature. And again, remember that what they're giving you is the y value and asking you what's going on in terms of the x values. Any comments or questions about that?
I'm good.
Okay. Okay, and then we're going to move on to application. So the whole rest of this section is all about applications that are lines. This is really handy for everybody because we're going to do linear functions a lot in your future. So comes in pretty handy. So example 4 talks about the monthly cost in dollars of a certain cellular phone plan. They don't do this anymore. They all went to those unlimited plans. But in the beginning, the cell phone plan was based on the number of minutes used. So it says the cell phone plan is given by the function c of x is equal to 0.3x, 38x plus 5. They then go on to tell me where x is the number of minutes. So the input value is the number of minutes used. The output value then is the cost of those number of minutes. So if you talk for 10 minutes, you can figure out the cost of 10 minutes and so forth. So part A says, what's the cost when you talk on the phone for 50 minutes? So if I talk on my cell phone for 50 minutes, what would have been the cost underneath this plan? So we're going to do that 50.
Plug it into the x.
Yep, that's exactly it. So we're going to replace x with that 50. Replace x with 50. So we'll have c of 50. So then be 0.38 times the 50 plus 5. And then you just head to your calculator and figure out what that is. And I got that to be 24. So this is saying if you talk on the phone for 50 minutes, it's $24. And it's a good thing we don't do this kind of plan anymore. Well, I don't know, we don't talk on the phone that much. We actually text on the phone and surf on the phone. Part B on that one says, suppose your monthly bill is $29.32. How many minutes did you use the phone? So this time, what are we going to do with that $29.32?
Set it equal to and solve.
Beautiful. So it's the c of x, or we're setting the function equal to it. 2 different ways to say the same thing. Nice. Yay. So 29.32 equals the 0.38x plus the 50. So we'll go ahead and move the 50 because now we're going to solve for x. Did I write that down? Yeah, 24.32. Negative 24.32. Wait, where did I get a 50? That's a 5. The negative made no sense, and I didn't catch that until just now. We're subtracting 5, not 50. Don't make up your own problems. That gives me 24.32 is equal to the 0.38x. And then we'll divide that out. The 24.32 divided by 0.38 comes out to be 64, and that would be measured in minutes. So if you have a $29.32 bill, then you know you talked for 64 minutes. Okay. And then to tie in the inequality idea, suppose that you budget yourself $60 per month. What's the maximum number of minutes that you could talk? So if 60 is the most you can spend, then what you do has to be less than that, because that's the most you can spend. So instead of putting in an equal sign, we're going to put in a less than sign, because again, the 60 has to be bigger. I'm sorry, you can't go above the 60. Does that make sense in terms of the inequality, or should we pop that one around? So this is the most you have to spend. So is that the right inequality there, or should we have a greater than?
I think it's, yeah, because your 60 is your budget.
So 60 is the top that we can use, so the 60 has to be larger than what we can spend. We must spend less than the 60. I think that makes more sense to say it that way. So what we're spending has to be smaller than 60. And now we'll go ahead and solve that. So 55 is going to be greater than the 0.38x. And then when we divide that out, x then is smaller, which makes sense in terms of what we're doing. And I got 144. And again, that's in minutes. So, and I'm sure that I rounded that. I think it gave me a decimal and I rounded that down. You can't go above that. Any comments or questions? Now I have an echo and I don't know why. Well, they gave us the function there. That was nice. Cost functions are just something to use because most people understand a cost function. So you see a lot of them. Our next example says, suppose that the quantity supplied and the quantity demanded of hot dogs at a baseball game are given by the following functions. So S of P stands for supply. So it's a negative 2,000 plus 3,000 P. And then D of P is equal to 10,000 minus 1,000 P. Okay. So S stands for supply, D stands for demand, and P is going to be the price of the hot dog. So the P in this function is the price of the hot dog. So I'm hoping that it makes sense that if this price of the hot dog is low enough, lots of people will buy it. If the price of the hot dog is, we'll supply lots of them and we will demand lots of them. And then if the price of the hot dog is big, then you're not going to have as much of a demand and you won't have as much of a supply. You'll notice that one of these has a positive slope of 3,000 P and the other one's got a negative slope of a negative 1,000 P. So in general, when you look at supply and demand equations, we don't need to graph them, but just so we know, one usually goes up and one usually goes down. This point right here that you're looking at, so let's see, our supply is going up and our demand is going down. That point right here where they cross is called the equilibrium point. It's the point of intersection between the supply and the demand. And if you take an econ course, which a lot of engineers have to take econ courses, Christina looks out as a future bet. She doesn't have to take an economics course. So I didn't enjoy my econ course. So part A on this one says, find the equilibrium price for the hot dogs and what's the equilibrium quantity. So what we're really graphing in terms of this function is this axis, the horizontal axis would be P, the price, and over here is going to be a dollar amount. I'm sorry, not a dollar amount, it's a quantity. It's how many of them we have. So if you input a specific price, you can figure out how many you need to supply and how much the demand is. So what they're really asking us to do in part A is to find that point. So we want to find point of intersection. So we're simply going to set those two functions equal to each other. So we'll do the negative 2,000 plus 3,000 P equal to 10,000 minus 1,000 P. So, okay, let's go solve it. I'm going to come in and move the P's to the left side to make them a positive quantity. So I'll add the 1,000 P over. That'll give us a negative 2,000 plus 4,000 P equals to 10,000. And then we'll move the 2,000 back. So we get 4,000 P equals 12,000. And then when you divide, you get a nice number. So it works out in the end. So 12,000 divided by 4,000 comes out to be 3. So what this is saying is that we're going to sell the hot dogs for $3 a piece. So the price of the hot dogs is $3. And I haven't been to a baseball game in quite a while, but I have a feeling that that price might be a little low. I don't actually know. I guess it depends on whether it's major league or not. They also want to know what's the equilibrium quantity. So in other words, if I sell them at $3 a piece, my supply and my demand are going to be the same, but we need to figure out what that demand and supply is. So what's our quantity going to be? So we're going to take that 3,000. You can plug it back into either of the equations because they're meeting here. It's not going to matter. You can plug it into either one of them. So I'm just going to pick the supply one. So I'm going to find S of 3. So that would be a negative 2,000 plus 3,000 times 3. Well, 3,000 times 3 is 9,000. Negative 2,000 plus 9,000 gives me 7,000 hot dogs. So if I'm the vendor who is selling those hot dogs, I need to bring an estimated 7,000 hot dogs whenever the supply and the demand are equal to each other. So if we were to write that point out as coordinates, that would be the point 3, 7,000. You're going to do a very similar problem that's got t-shirts at a concert, I think it is. But okay, that's part A. Any comments or questions about part A? No. Okay. Part B puts a slightly different twist on it. So part B is asking us, determine the prices for which the quantity demanded is less than the quantity supplied. So part B says the quantity demanded, so when is the demand less than the quantity supplied? So where is the demand less than the supply? So I could go through and do the whole thing again, but I'm going to try and let the concepts work for us here. So let's go back to my quickie graph over here. How did I know which one was which one? Well, I went off the slopes. So the supply had a positive slope, which means it's increasing. The demand has a negative slope, which means it's decreasing. So what they're asking for in terms of that, we already know that point. We already know that this occurred at 3, and then over here was our 7,000. They want to know when is the demand less than the supply. So we labeled the demand as the one that's going negative slope. We want to know when it's below the supply. So isn't that true anytime that we've got more than the price of 3? So in other words, if you make the price higher, doesn't the demand decrease? And then you end up with a surplus supply. And that's all tied together. So you could go back through and solve this. So in other words, you could set the 10,000 minus 1,000 less than the negative 2,000 plus 3,000. We're going to let the graph work for us. We know when the price is greater than $3, that the demand will be less than the supply. That's a dollar sign. Just going to take it out of there because it doesn't look like it. So whenever the price is greater than $3 per hot dog, the demand will be less than the supply. Okay. So does that make sense in terms of just logic more than anything else, I guess?
Yeah.
Yeah. So basic economics. Okay, only one more. It's a really short section. It should be a nice short assignment for you guys. Okay, this is example 6 on my handout. So it says, suppose that a company has just purchased a new computer for $5,000. So we bought it for $5,000. Must be a little bit better computer than what I get. The company chooses to depreciate the computer, and depreciate means that in terms of claiming it on your taxes, it's worth less and less each year because it gets lower and smaller in value, using the straight line method over 4 years. So we're going to depreciate over 4 years. And then we're going to assume that the scrap value of the machine is 0. So at the end of 4 years, its value is 0. And that's all they tell me. Well, that's enough, believe it or not. Part A asks us to write a linear function, but I'm going to actually go do part B first. Part B is asking me to graph the linear function. You're saying, well, how can I graph it if I don't even have it written yet? Well, we're going to use logic again to graph it. We know it's a line. In terms of the variables, time is always on your horizontal axis. Anytime a function involves time, it's always the horizontal axis. And that makes sense because the time is the one thing that we know is going from left to right, moving forward, getting bigger. The other axis over here is going to be the value of that computer as time progresses. Okay, well, what do we know? Well, we know that when we bought it at time 0, right, that it was worth $5,000. So right up here, I'm going to have a point at what, 0, 5,000. I know that 4 years later, it's worth nothing. So over here, I'm going to have an x-intercept at 0, 4. It's worth nothing. And the graph is going to do something like that. So without even having the function, I know what the graph is going to look like. The reason I tend to do it in this order is because I can now use these 2 points to help me write the equation of the line. So now I'll backtrack and find that linear function. So to do that, the first thing I need to do is to find the slope. So we're going to find our slope. So we're going to use that y2 minus y1 over x2 minus x1. So y2 is, whoops, don't do this. This is bad, don't do this. And I didn't recognize that I flipped him again until I got to that point. It should be 4, 0. And in a minute I was going to have a huge problems because of my change in y's. So now my change of y is 0 minus 5,000, which does make more sense. Sorry about that. Blame that on a Monday morning. Over the change in x, which is going to be 4 minus 0. So that gives me a negative 5,000 divided by 4. Because it is an application problem, I'm just going to divide that out and take that to whatever it comes out to be. It's not a decimal, it could have been, but it gives me negative 1250. Now, what that represents is how much this computer is decreasing in value each year. So in the first year, it drops 1250, the next year it drops another 1250, the next year another 1250 till the last year where it's worth nothing. Okay, so now we're going to go back to f of x equals mx plus b. So for us, I'm going to go ahead and call it v for value of x. So v for value, you can call it f, it doesn't really matter. Our slope we know is a negative 1250 times x plus the y-intercept. Well, we know the y-intercept. It's up here at 0, 5,000. So we know the y value is 5,000. And now we have a linear function. If you tell me how old it is, I can tell you what the value is. So this is what your accountants do for you, is figure out the depreciated value of the equipment in your business. So, yay! Much easier to graph it first, though. Okay, part C asks us, what's the book value of the machine after 3 years? So at this point in time, what's the value over here? So what we're going to do is just plug 3 in for x into our function that we just found. So part C, no, this is part C, the graph was part B. The value after 3 years. So when x equals 3, what's the value? So v of 3 is equal to a negative 1250 times 3 plus the 5,000. So 3 times that negative 1250 is a negative 3750 plus the 5,000, which leaves you with 1250, which should make sense, right? I mean, you can walk this through just in terms of logic and get there. So we know that after 3 years, the machine's only worth 1250 on my taxes. And then the last part, part D, asks us, when will the machine be worth 2,500? So when will the value be 2,500? So am I plugging 2,500 in for x?
No.
No, we're setting the function equal to that, because that'd be 2,500 years, which doesn't make sense for anything. So we're going to set the function equal to that 2,500. Again, you probably have already got an answer numerically in your head without having to go through the algebra behind it. When you move the 5,000 over, we're getting negative 1250x equals a negative 2,500. And then we'll just divide out the negative 1250 and get the 2 that you already know the answer is equals 2. So after 2 years, the value of the machine is only half of what it was to begin with. So, and those are the linear functions. They're pretty straightforward, but the most part, they're going to give you the function, but you do have a couple of problems where you have to write the function and then use that to solve stuff. So, okay, any comments or questions about our linear functions?
Nope, I'm good.
Good.
Yay,
Nice and easy.
fantastic. It's a nice, yeah, it is a nice, easy beginning section for this chapter. I really like it. So, okay, that honestly is it. Don't forget to get your exam scheduled, please. And it emails me when you do that, so I will know that you've got it scheduled. So start doing that. Figure out what your weekend's going to be like when you can take that exam. The exam's open Friday through Sunday, so anytime in there is good to go. Okay. Okay, have a great day. Enjoy it.
Thank you, you too.
Thank
Stay
you.
cool. Bye-bye.